I thought it'd be nice to look at a concept that is quite important in quantum computing and is one of the fundamental blocks in achieving quantum error correction in order to build actually a fault-tolerant quantum computer. And that is mid-circuit measurements. In doing any type of computation, what you're doing is applying a series of operations. Addition, subtraction, and you have similar ones in quantum circuits as well. For example, what might be commonly known as the NOT gate in a classical computation is the same thing as a poly X gate in a quantum operation. And similarly, there's similar analogies for other types of gates as well. And by performing many of these gates together, what you hope to achieve is to manipulate a quantum state from one state to another. You have a starting point, and you want to reach some arbitrary solution. And at the end of that, you want to be able to say that, oh, you have the right solution or you have the wrong solution. In order to do that, you need to have all the essential components of a quantum circuit. You need to have a known initial state. So what it matters how you initialize your quantum state before you start doing any quantum operations. And then you have the operations themselves, essentially what you do to the quantum state along the way as you're performing different types of operations. And then at the end, you have what is called a measurement. We try to basically determine what your final state is, whether it's the 0 state, the 1 state, and that tells you whether your quantum operation is performing as it should. Now, what I will hope to do in the beginning of this demonstration is to bring you through the general ideas of what a quantum circuit is meant to do. And what I'm going to use here is Qiskit, but really there's many similar programs out there. You can use Qiskit, you can use Circ, which is the Google one, or you can use any other coding platform that allows you to be able to manipulate this type of quantum circuits and do this type of simulations. So there's the standard import commands. I'll be importing things along the way. So I would say that you can import just the basic ones like NumPy and Qiskit, and it will suffice for now. And in Qiskit, how you define a quantum circuit is by starting with the command of quantum circuit. So what this does is that it allows you to define basically the number of qubits. Qubits in this sense are basically quantum bits, right? So these are you can think of them as different entities that have a certain property that you're interested in. In this case, they can be either in the state of 0 or the state of 1, right? And what this command does, or this line of code does, is essentially you are telling the program that I'm going to start with 2 of these qubits, both starting with the state 0, right? And you can see that if you print out the qubit states, that is exactly what it says, right? You have 2 qubits with indexes 0 and 1 that starts in the state that you desire. And what I will show next is some of the basic operations that you can attempt to do on the qubit. Now, some of you might be familiar with what is called a block sphere, some of you might not. I will try my best to use that as a tool to explain what I'm trying to do here, right? So a block sphere is essentially a diagrammatic way to explain how a qubit can move, can change with different states from 0 to 1 and 1 to 0, for example, right? And if you think of a sphere like this, and if you think of the top state as the 1 state and the bottom state as the 0 state, essentially what that tells you is that in order to move from one state to another, what you're doing is a rotation on the surface of the sphere, right? And if you think of it as a 3-dimensional space, you can see that basically, depending on how you choose to rotate the state of your qubit on the surface of the sphere, you can either rotate in the X, Y, or Z directions. And there are ways to combine these rotations along these directions in such a way that you can go from 0 to 1 or to really any other position on the sphere itself. And that represents essentially a different quantum state. And what I'm trying to show here is different type of rotations that you can perform about the X, Y, and Z axis. So for example, if you have a state that starts like this, pointing towards 0, a rotation about the z-axis would do nothing to it because the z-axis is pointing along the same direction, while rotation along the x-axis that is here would rotate it about the axis, right? In fact, it would do this, right? And so that's what I'm trying to do here. Here, what I have is a rotation about the x-axis, and I can also define the angle I would like to rotate it. If you do a 2 pi rotation, it'll be a complete rotation about the sphere. And in this case, half a pi rotation is the one that brings the qubit from the state pointing to 0 to somewhere on the equator of the sphere. Similarly, you can do the same with a z rotation, and I've repeated it here. Now, note that I've also added what is called CX gate. So this is what we call control X gate, or C0 gate. So this, now we have gone into the realm of 2 qubit gates, right? So previously, what I was describing with the block sphere was essentially how you perform single qubit gates in various directions about the sphere. Now with 2 qubit gates, there isn't an easy way to illustrate it that way. But in this case, what's really important for you to understand a 2 qubit gate is essentially that now what you have is a gate that operates on both qubits, right? It's not just operating on one of them independently of the other. Now the 2 qubits will change their position on the block sphere depending on how each other change, right? So what the CX or C0 gate does in this case is depending on whether the one state is in the 0 or 1, whether one qubit is in the 0 or 1 state, decides to flip or not to flip the other qubit. So the way to summarize it is if qubit 1 is in the 0 state, qubit 2 does not change its state. So if it was in the 0, it remains 0. If it's in the 1 state, it remains at 1. But should qubit 1 be in the 1 state, qubit 2 will actually flip its orientation. So if qubit 2 was in 1, it now goes to 0, and vice versa. And that's exactly what this gate does. And I've chosen an arbitrary arrangement of these gates, but let's look at how they actually look in practice. So if I were to use the Qiskit draw command, it will actually allow you to basically illustrate the gate. So this is an inbuilt functionality within Qiskit as well. So you can tell that now on this diagram is exactly what we have defined earlier, right? Where we have a pi on 2 x rotation, a pi on 2 z rotation, followed by a C0 gate, a pi on 2 z rotation, and pi on 2 x rotation. And these are how the gates are represented in Qiskit. Now, as I was saying at the beginning, there is generally three different components to a quantum circuit: the initialization, the operations, and the measurement. Now let's see what happens when we try to measure that. When we try to measure these states, what happens is that there is a projection of this state onto a classical bit, depending on where it's the 0 qubit or the 1 qubit. And at this point, it is relevant to our understanding that if what this does is essentially that if your qubit was in the 0 or 1 state, the classical bit will also act exactly as it should, right? You'll be in the 0 or the 1 state respectively. Now what happens if the qubit is in a superposition state, meaning that it's somewhere on the block sphere along the equator. Now it is in a superposition state between 0 and 1. So what that means is that there's a certain probability of the classical bit being 0 or 1. And the way I like to see it is that depending on where your qubit sits on the block sphere, if it's here, it's always going to read as 1. If it's here, it's always going to read as 0. And in the middle, it's going to be 50-50, right? And depending on how far away it is from equator and how close it is to either 0 or 1, it's going to read a slightly different state. And there's always a probability. And this is probably the bit about quantum that's most confusing and fascinating at the same time, I would say, is the fact that a lot of the way we understand how quantum computing works in general is via its probabilities. Now, what I've tried to illustrate here is essentially the different components that we could have in a quantum circuit. Now, we also want to visualize slightly more than that, right? As I said, with quantum circuits, there's always a component of probabilities, right? It's not enough to look at the quantum circuit once and say it's in the 0 or in the 1 state, right? Because the result could be different every time you perform the circuit. And within Qiskit itself as well, there are functionalities that allow you to simulate these probabilities and be able to visualize how these probabilities will work. And in the next few minutes, I will hope to illustrate that. And in the code itself, it is important that now you need to import a few more functionalities. What I've imported here is essentially the simulator and the plotting functions that will allow you to plot the histograms easily. And what I also try to illustrate here is how complicated the circuits can get, right? So in the earlier examples, we were working with 2 qubits. There was just one single qubit gates and 2 qubit gates, and you could see how exactly they relate to each other, possibly just by intuition. But once you have a much larger system, it can get complicated. So for example, what I have here is a quantum circuit that has 5 quantum bits and 5 classical bits. And the reason why I created the 5 classical bits is just so that I can read out each of the quantum bits individually onto the classical bit that I wish. And I've chosen a random series of gates here that includes single qubit X rotations, single qubit Y rotations, as well as single qubit Z rotation. And I've also chosen to apply at random 2 qubit gates. So here you can see that there are CNOT gates that I've applied here. I also chosen to apply what is called CZ gate. So this is instead of gaining a flip from 0 to 1 or vice versa, depending on the state of one of the qubits, you gain a phase instead. So instead of flipping up from 0 to 1 or 1 to 0, what you get is a rotation for the z-axis, and there's this gate here. And in fact, you can also define arbitrarily many multi-qubit gates. Like here, I've defined what is essentially a controlled NOT gate. There's a NOT operation dependent on the state of 2 other qubits. So this highlights almost the importance of having good visualization as you try to increase the number of qubits that you are looking at, as you try to increase the number of qubits and the operations that you are trying to simulate in Qiskit or whatever program you wish. What you're going to get is more and more complicated series of gates, more and more complicated series of operations. It becomes really, really difficult to understand what you're trying to do with these operations. And visualization becomes really, really important there. And this is also what I would like to highlight as part of Aaron's journey in trying to understand more about how quantum computing works. I understand the audience can come from a wide range of backgrounds, but regardless of whether you are completely new to the field and just learning this out of interest, or whether you are someone relatively experienced and trying to explore new ways to do simulations, it's important to look at this as how can you utilize this test bed to its maximum ability to tell you information, right? And visualization is very important. And as I will show towards the end of this presentation, choosing to visualize it in complicated ways and being able to visualize it as a function of different type of parameters becomes especially important as you try to understand more and more complicated concepts. And what you'll notice is at this point, I've not quite gotten into the main topic of what I want to talk about yet. Here, all we have is the initialization, our operations, and the measurement at the end, right? And just to illustrate the measurement itself, it can be as complicated or as simple as you want. Here, I will try just a simple example. I've performed a series of random gates, and what I want is now I want to find out what's the state of qubit 0 at the end of this circuit. So I perform a measurement that is done via this line of code, and I just draw the circuit diagram just so that you can see how it looks. And now, using a simulator that I loaded earlier, I can do a simulation of the probabilities and see how it looks via histogram plot, right? So what I'm doing here is I'm loading a simulator that performs the circuit and just calculates its probabilities, and I run it for about 1,000 shots and get the results out at the end. And what this is saying is essentially, if you just print the numbers, what it's saying is that out of the 1,000 shots, about 478 of them shows this state and 546 of them shows this state. Note that in this configuration, the convention is that the first qubit, or qubit 0 in this case, is at the end of the qubit bit string. And this is about 50-50, right? And you can see that via the histogram that is about right. In this particular case, it is meant to be 50-50, but with this type of simulations, because it's a probabilistic thing, depending on the sample size, which is the total number of shots, it can deviate. Of course, as you increase the number of shots to maybe 10,000 or even 100,000 shots, it's going to get closer and closer and closer to 50/50. You could try that, of course. I did just 1,000 shots here out of interest of time. And you can also do the same with a simpler circuit, just to make sure that we are getting the result that we want to see. And that's what I've done here basically. I've loaded the same number of qubits, but now I'm just saying, let's just look at the simpler gates. Let's just operate X rotation on one of the qubits and the Y rotation on the other qubit. And now it's going to get perhaps a bit complicated. Here, I'm going to start introducing the idea of doing a mid-circuit measurement. Now, a mid-circuit measurement by definition is a measurement that allows you to read the state of a target qubit while not destroying its state, allowing further operations to be performed with it, right? So in principle, this is not quite a mid-circuit measurement, right? Because what I'm doing is essentially, I'm operating on the qubit for a certain amount of time. I'm just measuring its state, and that collapses the qubit state into being the same as the classical state, right? And it loses its containers, which is not what you want. You want it to maintain any entanglement or superposition they originally had. But here, what I'm trying to illustrate really is how you can do multiple measurements in a quantum circuit simulation and look at some of the results that you would expect. So here, what I've done is, let's focus on just the operations I've done on the qubit 0. I've started with a pi on 2x rotation, which brings it from the 0 state to the equator of the state. Then I measure it. In this case, because it's on the equator, it's going to be show results that are 50/50, 0, or 1. Now, all of this is still making sense. Let's try something else. What if instead of a pi pulse, I do a pi on 2 pulse here? Note that this is exactly the same circuit that we were looking at before. Now what happens? If this root was a 0 state, it just gets rotated to the equator again, and this becomes 50/50. And if it was a 1 state, it also gets rotated to the equator, and this becomes 50/50. Now let's just think about this for a minute, right? Previously, what happened was that the classical bit 0 and classical bit 1 had to be different because of the pi pulse between them. But now, because I always rotate them to the equator before doing the measurement, there's always a 50/50 chance of reading each of them out. And therefore, I should get a 50/50 proportion for each of them, meaning that now there is a 25% chance of every possible combination, which is a 0/0, a 0/1, 1/0, and 1/1. And now let's take a look at the simulation. That's exactly what we see. Both classical qubits 1 and 0, as defined in this case, and this leads to 25% probabilities across the board. And now in this case, I've tried to repeat the same thing, but now I've simplified the circuit just for ease of interpretation, as I've mentioned before. So I was going 5 qubits for the sake of showing how complex the circuit could be. But to really understand the results, starting from the simplest case, you want to actually start with the simplest case, which is exactly what we have here. And you're going to get the same result. It's the exact same simulation as that we've chosen to simulate less qubits. The other qubits in the previous simulation were not involved in the measurement anyway. And you can try all kinds of possibilities. Right here, I've tried to make it confusing in some ways by reading out the state to the same classical bit, both to the 0 classical bit in this case, and what you're going to get is 50/50, right? Because you're essentially reading out to the same bit, so classical bit 1 is always going to be 0, right? So that's this one and this one. Well, either of these cases, you're going to get a 50/50 proportion of classical bit 0, which is this one and this one. Now, this is where mid-circuit measurements come in, right? The whole idea of mid-circuit measurements, as I was saying, is to be able to do a measurement in the middle of your circuit without disrupting the target qubit that you care about. And the way to do it, in the simplest of cases, is to do a CNOT gate between what is called a target qubit and what is called an ancilla qubit. So the ancilla qubit in this case is meant to be the qubit that just stores the information from the target qubit, and the ancilla qubit is meant to be measured so that the target qubit can continue to have operations applied as if it was never measured. And really, this is a topic that can get really, really complex, and there's loads of references out there and papers out there that talk about this. But here, I'm just going to go with as simple example as possible. And so what I do here is I apply a pi-on-2 pulse to a CNOT, another pi-on-2 rotation, and I read out each of these qubits to their corresponding classical bits. Now let's look at what we get in the simulation. We get what is basically 25% probability of every possible state. Now let's think about it for a minute to understand how that is the case. When we do a pi-on-2 gate on qubit 0, rotate it to the equator. And now we do a CNOT gate. As I was saying, the CNOT gate is a gate that does something to the ancilla qubit if the target qubit is in the 1 state, but nothing if it's in the 0 state. So if qubit 0 is on the equator, half the time it's going to cause qubit 1 to flip, and the other half is not. Exactly as you would expect, qubit 1 is in a 50-50 superposition, or rather has a 50% chance of being in the 0 state or being in the 1 state, because the qubit 0 was 50-50 in 0 or 1. And now you apply another pi-on-2 gate to qubit 0. Now this gets interesting, right? Because then you might think, oh, but it was on the equator. If I just do another pi-on-2 rotation, doesn't it just go to 1? Why do I still get qubit 0 in the 0 state? That is because this forms what is called entangled state between qubit 0 and qubit 1. And this concept of entanglement is really what makes quantum physics interesting and different from what you usually see in classical physics. Here, because qubit 0 and qubit 1 forms an entangled state, by measuring qubit 1, you also project qubit 0 into a particular state. So whenever you measure qubit 1 to be in the 0 state, qubit 0 also gets projected into 0 state. And when you measure qubit 1 in the 1 state, qubit 0 gets projected in the same state as well. Now, this is going to be an oversimplification of what actually happens. But essentially what that means is that even though you do a pi-on-2 rotation afterwards, you're still going to get a 50-50 chance of measuring qubit 0 in the 0 state or the 1 state, because of the fact that you entangle the 2 qubits and measure qubit 1. And therefore, you're going to get equal proportions across all 4 possibilities. It's a really fascinating topic that, to be honest, even in my daily life, when I talk about this with my colleagues, it gets really, really complicated. So if you're confused now, that's completely normal. Again, my suggestion is to play around with the possibilities, try different gates, like what I've done here. Now I've tried to, instead of doing a pi-on-2 rotation, let me just do a pi rotation and see what it does. And now you see that it's going to be 50-50. Yeah, and now we get a 50-50 proportion because of the fact that this gate has changed. And really, I will encourage you to just try all types of combinations, like this ones here as well. And now you get a completely different answer from before, and you can even add noise into your Qiskit circuits, and all these noise models allows you to explore how these proportions to change because of noise. Now, I've added noise here to make the last part of our simulations easier, right? Because as you notice, if I were to just do this simulation, I only get counts in one of the states, I would not be able to easily get the counts of the other states, even though I know that they are 0, right? So I introduce noise to make sure that all of the states are not quite 0, and so that I can actually put them in a for loop, like in this case, and iterate across the parameters that I've chose. So in the earlier examples, I was just playing around the angles, trying out different type of angles, and then rerunning the simulation. Now, what if I would sweep the angle from one value to another. In this case, I've chosen to switch from 0 to 10 radians, and I just repeat the same simulation over and over again and get this oscillation of counts of one of the states. And this gives you a sense of the rotation, right? Because here it was a zero, it was no rotation. And somewhere along the way, there was a pi rotation, there's a 2 pi rotation, and you get this sine or cosine-like structure as a function of the angle of rotation, right? You can tell that this probably corresponds to pi and this to 2 pi. And goodness, this was something that would have taken quite a while to run. So it's, as you can tell, I have stopped it, but you can always try with a relatively small number. Like here I've chosen just to sweep 25 different angles with the maximum angle being 15 radians. And now I've chosen to sweep both the angle before and after the C0. And what you can do is in fact plot a 2D diagram, something like this. And now you get a color plot that shows clearly the sine or cosine-like structure as a function of all of the rotation angles. And this is really fascinating because this is almost a visualization of physics, right? Because this is based on a plot like this, you can interpret different type of results and how you expect your desired parameter to change as a function of the different angles. And this is really all I want to show. At the end of the day, what I hope to show here is twofold, right? One is to introduce the basic concept of what a mid-circuit measurement is, but also show you how you can do your own exploration at your own pace for various different types of topics.
Okay, great. Thank you so much, Menge. That was really engaging and informative. So just a couple of questions. One question that I hear quite a lot actually from people who are in the very early stages of quantum programming. Many people, of course, refer to fault-tolerant quantum computing, right? And in fault-tolerant quantum computing, mid-circuit measurements are critical. So could you briefly explain a simple scenario where these measurements that you've just described to us would really help us to detect and to correct errors?
The main reason for needing this type of mid-circuit measurements is quantum error correction. And essentially what happens there is that you're going to have many, many qubits, some of which are going to be what is called a data qubit, which actually holds the data that you're interested in. And some of them is going to be called ancilla qubits, which, as I briefly mentioned earlier, are going to be the qubits that you are just going to measure, right, as a proxy for your data qubits. Now, at the end of the day, data qubits have a certain finite lifetime, right? In the case of spin qubits, which I'm familiar with, the typical lifetimes can vary from tens of microseconds to maybe a millisecond, right? These are not long times, but to do an actual computation, you might need the time to be much longer than that. And what happens with mid-circuit measurements is that you don't always have the luxury of waiting for the end of your circuit to know whether or not an error has occurred or your circuit is doing the right operation, whether your qubit is in the right state. And therefore, a mid-circuit measurement, in my simplistic view, is really almost like a periodic check of your quantum state to basically say, okay, am I on the right track? If I am, good. If I'm not, let's do a correction, right? It's almost like I see it as a way, almost the lens to look at the quantum circuit itself without disrupting it, right? So yeah, that's really the role that mid-circuit measurement play.
And would you say there are maybe some hardware limitations, at least right now, or timing constraints and such that could make such mid-circuit measurements particularly challenging? And how do current platforms deal with that challenge?
Yeah, and that is a very, very good question because as I alluded to, the qubits that we are working with has limited lifetimes, right? Everything has to be performed within a certain time for it to make sense. I would not say that I'm familiar with all qubit platforms, but I would say that in general, this is basically the question that everyone's trying to answer, right? How do I perform mid-circuit measurements quickly enough in a way that the measurement itself does not actually cause problems for my qubits? And this is a very timely problem for spin qubits as well, because our times for measurement are sometimes comparable with the times there are the lifetimes for qubits. That makes mid-second measurements, to be blunt, useless, right? Because if it takes a second for the qubit to lose its coherence, and it takes a second to also read out its state, then what's the point? You know its state, but it's now a classical bit and cannot do anything with it anymore. And the challenge there, to me, means that we can solve it in two ways, right? One, you work on improving your electronics, your instruments, or maybe your measurement technique as well to shorten the length of your measurement time, or you can engineer the physics of your system to improve the lifetimes of your qubit. And every platform has a slightly different way of doing it. Sometimes all it takes is simultaneous operations by some engineering techniques. Sometimes it's just having more qubits sometimes help as well. It really varies across platforms. That's for sure.
Great. All right. Well, thank you so much. We're at the end of our show. And thank you, Mege, for joining us today and for giving such a great session. And thank you to our viewers. Feel free to like and subscribe. Thank you so much and goodbye.
Thank you.